Let's see how to calculate arc length when a curve is described parametrically. So a parametric curve has equations that look like this. X is a function of t, and y is a function of t, and t ranges from some point A to some point B. Recall that our formula for arc length for a function where y is equal to f of x looks like the integral from x1 to x2 of the square root of 1 plus the derivative dy dx squared dx. Now this formula, this familiar formula, hopefully it's familiar by now, can be translated into our parametric form pretty easily. Recall that the derivative dy dx is equal to the derivative of y with respect to t over the derivative of x with respect to t. So let's start by taking this expression and substituting it into this formula where we have dy dx. We get s is equal to the integral from x1 to x2 of the square root of 1 plus, big parentheses, dy dt over dx dt, all squared dx. Now, this is pretty messy because we have a fraction squared inside the radical added to 1. So what I'd really like to do is to combine those two terms inside the radical using a common denominator. Let's go to the slide. So we had 1 plus dy dt over dx dt squared. So let's replace this 1 with dy dt. Let's replace this 1 with dx dt over dx dt squared. Now this whole thing is equal to dx dt squared plus dy dt squared all over the common denominator dx dt squared. And remember that this was all inside a radical sign, right? This was in a radical. So the denominator can come out of the radical and lose its square. So where are we now? Now we have the integral of the square root of dx dt squared plus dy dt squared times 1 over dx dt. Now the convenient thing that happens next is that as we change the variables from dx to dt, since x is a function of t, dx is dx dt times dt. So instead of the dx, I'm going to put dx dt times dt, and now instead of our limits going from x1 to x2, we're going from t equals a to t equals b. We've done a change of variables, kind of like a u sub. And the nice thing about this is this guy all gets canceled out because we have a 1 over dx dt times dx dt. And so what are we left with but this beautiful formula, the arc length is equal to the integral from t equals a to t equals b, from t equals a to t equals b of the square root of dx dt squared plus dy dt squared dt. So let's make a note of that formula and let's see how to use it. So let's apply that formula to the following situation. Let's consider the ellipse described by the following equations. X is equal to 3 cos theta, y is equal to 4 sine theta, and this ellipse starts right here on the x-axis at 3, 0, and it travels along in this direction. It hits 0, 4, keeps going to negative 3, 0, 0, negative 4, and it's over here when theta is equal to pi, and it gets right back to the beginning when theta is equal to 2 pi. So if we want to know the circumference of this ellipse, or the distance all the way around, starting here and moving all the way around this ellipse, basically what we are looking for is the arc length of this curve. X is equal to 3 cos theta, y is equal to 4 sine theta, and t ranges from 0 to 2 pi. So all we need to do now is apply our formula. So we need dx d theta. That's the derivative of x with respect to theta. That's a negative 3 sine theta. And we need dy d theta, which is the derivative of 4 sine theta, so that's 4 cos theta. And the arc length is going to be the integral from 0 to 2 pi of the square root of this squared, so that becomes 9 sine squared theta, plus this squared, that's 16 cosine squared theta, d theta. And this is one of those situations where your calculator or your computer is going to come in handy. You use the integral feature of your calculator, and you should get that the distance around this ellipse, the circumference or perimeter of this ellipse, comes out to be 22.103. Well, that wasn't so difficult.